Hello, everyone. I am Pranav Atreya, and welcome to my presentation on state-supervised steering function for sampling-based kinodynamic planning. This is joint work between myself and Dr. Joydeep Biswas, and was conducted at the Autonomous Mobile Robotics Laboratory at UT Austin. I'll begin with some motivation as to why kinodynamic motion planning is an important problem. The goal of the general motion planning problem is to develop an abstraction of the robot and the robot's workspace, and then compute a plan for the robot that takes it to the goal while respecting the constraints of the abstraction. Geometric planning is one example of such an abstraction. In geometric planning, the robot is abstracted away as a point in a configuration space whose dimensions correspond to physical attributes of the robot, such as its X position or orientation. To plan paths, algorithms like grid search shown in figure A or RT star shown in figure B can be used. Sampling-based planning algorithms like RT star work better for high-dimensional systems as they don't suffer an exponential computational blowup. Geometric planning as an abstraction faces several drawbacks, however. One of the assumptions in geometric planning is that arbitrary configurations of the robot can be connected by a straight line through the configuration space. This is only a valid assumption for holonomic robots. Additionally, geometric planning does not take into account the dynamics of the robot. One solution is to simply ignore the kinematic or dynamics constraints and plan paths with geometric planning anyway. The problem is that the resultant plan is likely not at all useful because the robot may not be able to physically execute that plan due to its motion constraints, or the plan may only take the robot in a limited range of its motion capabilities. Hence, we turn to kinodynamic motion planning, a more powerful abstraction that can take into account both the robot's kinematic constraints and its ability to execute motions of varying velocities and accelerations. Like with geometric planning, some of the most powerful approaches to solving the kinodynamic motion planning problem are sampling-based planning approaches. Two notable asymptotically optimal algorithms are RT star and BIT star. To ensure optimality, however, these algorithms require access to an optimal steering function. An optimal steering function takes as input a start state XA and a goal state XB, and returns as output a control sequence. This control sequence, when executed on the robot, should take it from XA to XB in minimal time. Computing the optimal steering function in an efficient way is, however, quite a difficult problem. There exist closed-form solutions typically only for a limited class of robots, typically robots whose kinodynamic constraints are linear. In the general case, computing the optimal steering function amounts to solving a two-point boundary value problem. These two-point boundary value problems are typically solved by nonlinear programming solvers. The main drawback of NLP solvers is their computational cost. For complex kinodynamic systems, they take up to the order of a few seconds to compute the steering function. To address the difficulty in computing the steering function required by optimal sampling-based planning algorithms like RT star, some related works avoid computing the steering function altogether. These works can theoretically find either asymptotically optimal or asymptotically near optimal solutions to the kinodynamic motion planning problem. In practice, however, they tend to take a long time to find low-cost solutions. Another line of work tries to make computing the steering function with a nonlinear programming solver more computationally efficient by employing several optimization tricks. Despite this, however, the NLP solvers remain a bottleneck. Some approaches formulate the kinodynamic motion planning problem as a Markov decision process and find solutions with reinforcement learning, and related approaches attempt a hybrid approach that combines learning with sampling-based planning. Finally, another class of approaches makes use of gradient-based optimization. Some notable works in this category include CHOMP and STOMP. A limitation of these works is that they typically can only find low-cost solutions if initialized with a feasible solution near the global minimum. As a result of all of this is that fast and optimal kinodynamic motion planning remains an open problem. With this work, we aim to provide a solution to this problem. The key idea of our approach is that the steering function can be learned. Rather than learning a function that directly maps to a control function that steers from a start state XA to a goal state XB, we formulate the control function as a piecewise constant control function and incrementally generate the piecewise constant controls. In this diagram, U1, U2, U3, and so on are constant controls, each executed for some predefined duration tau. Each of the constant controls is generated from a call to the learn policy pi, which takes in as input the current robot state and the goal state. By rolling out the policy pi, we can generate a length n sequence of controls that takes the robot to the goal state XB. Next, we discuss how the policy pi can be learned. The most straightforward approach is to supervise the generated trajectory rollout by the optimal trajectory rollout, which we denote here as T upper star. If we do this for a large number of different starting and ending states, we would have learned a steering function that can steer between arbitrary states. It turns out, however, that this approach, though intuitive, does not work. The reason is that the optimal control function for many kinodynamic systems exhibits behaviors of what is known as a bang-bang control function. They are called as such because the controls oscillate from one extremum to the other. An example of this can be seen in figure A, which depicts the optimal control function for a quadrotor robot. Learning systems struggle with modeling these stark discontinuities. In contrast, Notice that the optimal state function for the quadrotor is smooth and differentiable. State functions are guaranteed to be smooth because they are the results of integrating the kinematic differential equation of motion. Our insight is that a better way to learn the steering function is through supervision by the optimal state function, hence the name state supervised steering function. Learning the optimal state function is a much easier task because of its desirable smoothness properties. To actually carry out this learning, the state functions generated by consecutive calls to pi need to match the optimal state functions for a number of starting and ending states. It is important to note that pi still generates controls, but in this formulation, these controls are integrated to obtain a state function gamma, and the state function is trained to match the optimal state function gamma upper star. By training the state functions to be optimal, you're indirectly learning pi. This indirect learning scheme allows pi to learn a continuous version of the optimal control function, as opposed to in the previous setting, pi learning the original discontinuous optimal control. Next, I will discuss how S3F can actually be used for kinodynamic planning. It turns out that simply plugging in S3F as a steering function does not work. The primary reason for this is that the goal state in a steering function query may not be reached exactly by S3F. This can happen for one of two reasons. It may be that the selected goal state is not even kinodynamically reachable from the start state. It could also be that S3F returns a trajectory that reaches near the goal state, but not exactly at the goal. This behavior is an unavoidable consequence of learning-based systems. As a solution to this problem, we developed S3F RT star, a modification of RT star that enables compatibility with S3F. S3F RT star is equipped with two key modifications. First is a modified tree addition step that governs how newly sampled states can be added to the RT star tree. The second is a modified rewiring procedure. An important feature of the S3F RT star algorithm is that it is probabilistically complete, meaning the likelihood of it returning a feasible solution if one exists asymptotically approaches 1 with respect to computation time. We encourage viewers to read the paper for the full proof. Next, I will proceed to discuss the S3F RT star algorithm in greater detail. Assume the RT star tree contains some number of states. The first part of the algorithm involves sampling random state xrand and attempting to add it to the tree. Connections are attempted from all nearby states in the tree to xrand by making calls to S3F. Next, the algorithm picks as the parent state xparent, the state whose trajectory to xrand allows xparent to be reached at minimal cost. We deal with the fact that xnew, the terminal state of the trajectory to xparent, may not exactly equal xrand by simply assuming that xnew was the sampled state all along. Thus, we will replace xrand shown in red by xnew. With the sampled state now added to the tree, we begin the rewiring step. In the rewiring step, potential improvements to the optimality of the tree are considered by taking into account the newly added state's existence. We use S3F to steer from xnew to every other nearby state in the tree in hopes that these nearby states can be reached with lower cost by going through xnew. In this figure, we show this process for one nearby state, xtarget. Using S3F to steer from xnew to xtarget results in the blue trajectory. Assume like before, the xtarget is not reached exactly, and instead the trajectory ends at xterminal. We can no longer simply assume the xterminal was the state to be reached all along because the xtarget may have children states that need to be accounted for. To account for these children states, we make use of a rewiring propagation procedure. If we simply replace xtarget by xterminal, there will be a gap in the tree preventing all of xtarget's children from being reached. We deal with this gap by re-executing the trajectory that led from xtarget to xchild1, except beginning from xterminal instead of xtarget. This trajectory, which is a control sequence, was generated by S3F in some previous RT star iteration. We can make use of this trajectory without needing to call S3F again. The terminal state of the newly executed trajectory will be xchild1 prime, a state that is slightly shifted from xchild1. Once we have done this, we end up with a situation identical to the one we started out in, except here xterminal is xchild1 prime and xtarget is xchild1. Thus, it is easy to see that this procedure can be recursively propagated down the tree. Thus, the last part of this algorithm does exactly that, recursively propagating the rewiring to children states in the subtree. Here, xchild1 prime is to replace xchild1, and the trajectory that led from xchild1 to xchild2 is re-executed beginning at xchild1 prime. This trajectory shown in blue ends at xchild2 prime, which in turn will replace xchild2. To experimentally validate our approach, we compare planning with S3F RT star against RT, SST, and NLP RT star. RT is the ancestor algorithm to RT star, that unlike RT star is not asymptotically optimal, but can be applied to kinodynamic planning without a steering function. SST is a steering function-free algorithm introduced earlier, and NLP RT star is simply RT star with an exact steering function computed online by a nonlinear programming solver. We compare these algorithms on 3 robot platforms: the Humans core with acceleration, the tractor trailer, and the quad rotor. These 3 robot domains were chosen particularly because their kinodynamic constraints are fairly complex. The figure on the right shows a comparison of these 4 algorithms on the tractor trailer robot domain. The y-axis represents the cost of the best solution found so far, where lower cost is better. The x-axis represents planning time that is given to each of these algorithms. Each of these curves represents an average completed over 25 planning trials. The curve corresponding to S3 of RT star is outlined in the red box. S3 of RT star is able to find the lowest cost solutions and is able to do so quicker than any of the other algorithms. Given more computation time, it's also able to improve on its solutions, a highly desirable property. In contrast, the baseline algorithms like SST and RT find higher cost solutions and struggle to improve even when given more computation time. They also have higher failure rates, with NLP RT star not able to find a single feasible solution on any one of the 25 planning problems in the allotted time. The improved performance of S3F RT star over NLP RT star can be explained by the orders of magnitude less time it takes for S3F to compute steering function solutions than the nonlinear programming solver. The improved results over SST and RT can be explained by the fact that S3F RT star connects sampled states with a near optimal steering function, while the baselines connect sampled states with randomly sampled trajectories, which have no notion of optimality. Similar to the tractor-trailer domain shown here, S3F RT star outperforms the baselines on the Dubin-Scarlett acceleration and quadrotor domains, the results of which can be found in the paper. These are some of the planning solutions found by S3F RT star on the 3 robot domains. In each of these figures, the start state is shown in green and the goal state is shown in red. The intermediary gray states are states along the final solution path. The golden curves which connect the navy blue dots represent the edges and vertices of the full RT star tree. These visualizations show the complex kinodynamic constraints that must be obeyed. In figure A, for example, the robot is initially moving to the left, which explains why the optimal path goes up and around the obstacles instead of directly to the right. This concludes the presentation of our work. To briefly summarize, we have demonstrated how the optimal steering function required by sampling-based planners like RT star can be learned through a novel state-supervised procedure. We integrated RT star and S3F to yield S3F RT star, a provably probabilistically complete algorithm. And finally, we demonstrated that S3F RT star empirically outperforms baseline algorithms on both cost of solution and computational time for 3 challenging robot domains. We invite you to read our paper linked in the QR code. I would now be happy to answer any questions.